be to the public. Okay. So the main subject I wanted to talk about today is the issue of stocks and flows. So last time we introduced the notion of stocks and flows and modeling. First of all, what sort of modeling are we talking about? System dynamic modeling. Yeah. So it's a type of modeling where the building blocks are small in number, and the central ones, the sort of ones that are really critical are stocks and flows. So what's a stock? Thank you. Yeah, it captures the state of the system, captures the current situation, the status of the system. Stocks collectively define sort of the current situation. They're the memory of the system, we could call it. Say, what is the case right now? And flows or what? Yeah, the change, rates of change going on to that state. And the flows depend on the stocks, and the stocks, their changes over time depend on the flows. So the flows represent the verbs, the kind of things changing right now. And the value of a flow is a value of a rate. It's a change in some stock per unit time. So the fact that a flow in to us, maybe there's a flow in associated with immigration to a population stock. Population stock summarizes the state. How many people are there in the population right now? The flow says, okay, there are 10 people per day, say, arriving. So it's a rate of change associated with that. In general, a stock might have many flows. And a flow typically go from one stock to the other, but sometimes it doesn't come from it only goes to a stock, or it only comes from a stock. If that's the case, how do we draw it? We didn't really talk about that yesterday. But suppose we have a stock and we have a flow that comes into it. What do we draw for the other side of that? A cloud. Yeah. And similarly, we could have a flow going out. And all that means is it's going out to something, it's coming from somewhere we don't care to model. It's sort of outside the scope of the model. Similarly, it's flowing to some place we don't care to model. It's again, outside the confines of the model, outside the scope of the model. So we just are not going to model. It's not to say there's no place it goes to. No, it probably does. It's just, it's not the focus of the model. Yes, Kurt.
In really complicated stuff or system dynamics models, can those go to different parts of the same model, but you don't want to visualize it because it's too complicated?
Yes, thank you. Well, okay, sorry. Yes, they can. So in other words, like if you had a set of stocks, and maybe this goes to a stock, but you don't want to just, accrete it to an existing diagram. You want to put it in a separate place just because this is getting too crowded or too messy or whatever, right? Then you could go put it in a separate so-called view of the model and something like Benson, and you could actually have it depend still conceptually on this flow. So one thing that's a little bit confusing here for those who are interested in understanding some of the nuances with Benson is that I'm making sort of broad descriptions of these diagrams and so on, but I'm dealing with sort of simplified cases. The fact is, a given model in Vensim can have multiple views associated with it, and we might split up a given model onto multiple places. Conceptually, it's all one model. It's just for convenience, we place it visually in different places. Okay? And you can do that with flows, although it ain't as pretty. It turns out that Vensim doesn't make it really pretty to do so, but it works. It works well. It's a good question. Okay. So maybe I'll just show an illustration of that. Here's a whoa, oh no, oh, sorry folks, I thought I had opened the wrong version of Ensign. It was counting on that. No, I really want to open sort of the complete version of Ensign to show this. So this is, for example, is a larger model. There we go. This is what's called a West Nile model. So it has birds, it has mosquitoes, and it has humans. But this is just the core of the model here. And there's actually, whole other areas of the model that are specific to certain types of calculations. For example, things related to demographics or things related to risk behavior. But don't get fooled. These things are all, in fact, truly one model. It's just, for convenience, we place them in different places so we don't have to look at everything at once. Does that make sense? Okay. It's a great question. Any other questions right now about that? So we have stocks and we have flows. And I argued that there was a phenomenon of inertia in the sense that typically what we can change is the flows. So we can change how quickly people recover from an infection, or how quickly we discover people with undiagnosed diabetes, how quickly people can get onto a highway or what have you. You could change how quickly people are using water in a reservoir, conservation measures or what have you, right? What we could change, and we could change the amount of emissions. We talked about that example last time, emissions into the atmosphere. It may not be easy, but it's, ladies and gentlemen, in life we change the flows. But what determines the state of the system, what determines the dynamics, the behavior at this current time, ladies and gentlemen, is the stocks. That determines the rates of the flow. So it's the stocks that are sort of making things happen right now. And we can't magically typically go in and change the value of the stock. We could make the flow out really, really quick, maybe, or flow in very, very quick. But we can't instantly turn an empty stock into a high stock. We can't instantly turn a high stock into a low stock. So we can't instantly drain the CO2 in the atmosphere. Instantly. It takes time. We can't instantly, increase the amount of health service personnel available to treat, in a pandemic. We can't instantly drain the number of infectives in a pandemic. We go and find them and treat them. We operate on the flows, but it's the stocks that lead to the behavior. And so there's this inertia phenomenon. This phenomenon that it takes time, often, and more time than we'd like. And one of the problems is that we as humans tend to be very poor about reasoning about these sort of things. In other words, we tend to fall into the trap of thinking, well, because I'm modifying the flows a lot, I'm doubling this flow, I'm halving this flow, and I'm causing this new flow to come in. We think we can change things dramatically. And often we don't appreciate the time that it takes. That's one phenomenon. But the other phenomenon, which is even deeper, is that we ignore the feedbacks involved. Mm-hmm. We ignore the feedback. So we think we could change, So what happens is that maybe we go and decide, okay, we're going to put a bounty on coyotes because there's too many coyotes around. And we're gonna put a bounty on coyotes and drain the coyote stock. And so we start to, coyotes start to be shot because of this, because of the rewards provided to, bring in a coyote pelt or whether you get some money. And what happens in response is there's feedbacks involved. So you go and you shoot a bunch of coyotes, and there's fewer coyotes around, therefore there's more gophers around and other prey around, and that population grows. And then the coyote population, gets nurtured by all this extra availability of gophers and other prey, and it starts to rebound. Even with this hunting, you think, oh, we're going to hunt and it's going to solve the problem. Well, the system pushes back. That's its way of pushing back against these things. Similarly, it may be that we think we can, again, lessen the congestion involved in the highway by adding a few extra lanes so that people can get in quick, and that works for a little bit, but people find it more convenient to move out of town because of that, and therefore we have more people that need to commute, and therefore it turns out to be just as slow 5 years later. Just we've spent $200 million in the meantime building extra roads. So we could affect the flows, but we often do so in a way that doesn't really take into account the fact we're having to nudge this system. We're having to slow down that proverbial tanker that needs 2 kilometers to turn around. We don't appreciate that, and we say, well, why don't we stop? Because of this inertia of the system. Or we find ourselves fighting against these feedback loops. Okay? So we're going to see more about this, and we'll see sort of our first feedback loops today with first order delays. Mm-hmm. So there's kind of this inertia. It takes time to fill a stock, it takes time to drain a stock, and stocks are often involved in these feedbacks that are critical to system behavior. And here we are pumping at them with our flows, but if we don't understand the feedbacks and take them into account, or maybe even exploit them, we may end up in a Sisyphusian task. We're pushing that rock up the hill, and it rolls back on us. Or we're like King Canute. Anyone know the King Canute? That isn't taught these days. So King Canute ordered the sea back. So he said, he's the king and wanted the tide to lower. Wanted to order the tide to lower. And it wasn't lined with how things work. He ordered the sea to go back, and it didn't retreat. And I think a lot of times in life, if we don't understand how these things work, we find ourselves working at cross purposes with the system, whereas we could do a lot better if we understood how it works. So this modeling is all about how it works. Okay. So let's talk more about stocks and flows. So who here heard about a first order delay? No, brother video. Okay, so what's a first order delay? Yeah, divided by some time constant, or some sort of rate. So we could have a first order delay of they're in fact mathematically the same. It's just a matter of sort of how we phrase it. We could say it's divided by 2, or it's multiplied by 0.5, 1 over 0.2. What does that 2 represent? If we say it's divided by this time constant, why do we call it a time constant? What is that? That represents the mean time in that stock, the average amount of time it spends in that stock. Okay, so that's why we say like recovery delay. So who can identify some first order delays in this diagram? Okay, this is one. This guy is divided by that. Okay, how about another one? Sorry? Yeah, this one right here. It's another first order delay. Now, why you might talk about first order delay? It seems like you're talking about some arbitrary thing. Well, why do we care about those? Why do I make such a big stink about them? Yeah, that's true. So it's actually a So it influences model dynamics in some important way. So there's another reason. That's right. So it governs a lot of the flows here. It turns out that they're the building blocks. I mean, stocks and flows are kind of the most basic building blocks, but first order delays is kind of the next level up of building block. And a lot of these models are nothing more than string together first order delays for a lot of it and then a few fancy pieces. And that's what this model is. We have first order delay here, first order delay here, and then you have something a little bit fancier, a nonlinear component, where ultimately we have, well, tell me, is it first order delay linear or nonlinear? It's linear. It's the value of the stock divided by some constant, multiplied by some constant. It's actually linear in the value of the stock. If you took that up by itself, could we figure out, for those mathematically inclined, in closed form, could we write a formula down for how that varies, the value of the stock varies, if we took it out in isolation? Yeah, we actually could. We could solve it. Because it's a nice, tractable thing. It's a very nice thing. Now, that's but here we have a nonlinear component because it actually involves a stock times a stock, among other terms. Okay, so there's actually multiplication of two sides. And that doesn't seem particularly deep. Okay, well, so what? I mean, maybe it could be a stock plus a stock. Well, it turns out once you get these combinations in a nonlinear way like that, all hell breaks loose in terms of your analysis. Linearity is what allows you to analyze what's going on. It allows you to take apart the input to a system, sort of how you poke at the system. You could just take it apart into nice pieces, figure out how it responds to each of those nice pieces, and put it together, and you know how it responds to anything. Linearity is what allows us to kind of tease things apart, reason about each in isolation, put them back together. It's really nice for reductionism. You kind of know what the whole does just by knowing what it does to each of the pieces of how we interfere with it. With a nonlinear system, oh man, you don't know where to start about sort of taking apart the. You got to consider it as a whole. Sort of the whole is greater than the sum of the parts once they have nonlinearity involved. That's why we pay attention to it. That's why I say it's nonlinear in these two. It's significance. It means we can't just sort of look at it and say, I know what the solution to this is, and write down a formula for how this behaves. Instead, we have to solve it. How do we solve a model like this? We simulate it. We step it forward in time, step by step, and we compute what are the changes now, and that allows us to compute, in other words, what are the flows now, and knowing the flows now allows us to compute the stocks the next little bit of time, and then knowing the stocks allows us to compute the flows, and so and on she goes. Okay, so we have to simulate it. We can't just write down a formula for a nonlinear model. Okay, but first order delays are nice little pieces out of which we build up a stock, and if you learn to recognize them, ladies and gentlemen, you kind of learn how to parse a model. A model like this might look many pieces. I could throw up other models here as well. But if you learn how to, well, here, look at this. Look at this. This is what is afforded us by the inverted classroom. Take a look at these things here. Where do you see first order delays? Well, this is a complicated model of West Nile infection and so on. But there's actually quite a few first order delays. Mean time to this and this larval mosquitoes. Mean time to pupal maturation, these larval mosquitoes. Disease incubation, and there's a virus incubation rate by which they proceed here. These are just first order delays. Look at this, natural death rate and the number of mosquitoes. This whole model is just like littered with these first order delays. So if you learn how to recognize first order delays, often you end up seeing a model, it's like 80% first order delays. And I'm not exaggerating. I mean, it's actually like the bread and butter of modeling. And this is true regardless of whether you use system dynamics, which includes nice graphical depiction and software like this, or if you go to you know, ordinary differential equation modelers who write things only down, you know, in formal differential equations, ODEs. Often 80% of it is just first order delays. So if you know how to reason about a first order delay, you know a lot about how this model works. And it's also, ladies and gentlemen, perhaps the simplest little building block involves feedback. So, ladies and gentlemen, tell me, with a first order delay, so here we have a first order delay. Where's the feedback here? I thought Kurt might stride up here to show us. But, where's the first order? Where's the feedback here? This and then this, right? Remember we talked about this last time? What polarity would I associate between the stock and the first order delay for the outflow? It's a plus. You increase this, all other things being equal, this will increase compared to the value it otherwise would have had. If you have more people at risk of death, and all the things being equal, there's going to be rates of death than there otherwise would have been. What's the polarity associated with going from the outflow to the stock? It's minus. Hence, it's a negative feedback. Okay. So, narrate for me the implications of that in terms of suppose we have no inflow. Suppose we turn off the inflow, turn off this spigot. There's nothing coming in. What's the behavior of this stock? Suppose this stock has some large amount of quantity in it. What's the behavior of the stock over time? What does it behave like? Okay, so I'll try to draw it here. So tell me how it's reduced. So it starts high. Does it go down like this? It goes like this, and then like that. Okay. Something like that. Bingo. So why? Why does it exponentially decrease like that?
You mean from the graph, right?
Well, the graph reflects my my choice of vocations. I didn't go into art, and it has its aesthetic limitations.
The graph on the board.
Okay.
Yeah.
Sorry. So why does it go down faster at first and slower later?
Because the rate depends on the stock.
Okay. Bingo.
If the stock is zero, then it doesn't go up, so then it's zero.
Good. And if the stock is high, then the rate is high, and therefore it drains the stock quickly. So there's a higher slope early on, and as the stock gets drained, it's a lesser slope, right? And as time goes on, the draining is occurring less and less quickly, and therefore the stock is declining less and less quickly, right? And so you have this stock and flow sort of co-evolution there. That's quite straightforward. So let's go and yes.
I think I got it in my head.
Yeah.
It's more of a fundamental question.
Yeah.
That you started.
Okay. Yeah.
But I was having a hard time seeing how the rate was related to the stock. Like I come from a health science background.
Right.
So if you just have a population,
Yeah.
how that will affect the rate of disease. But I thought, well, it's a susceptible population. If you increase the number of susceptibles,
Right.
that will increase.
Precisely. So take people at, maybe this is normal glycemic people who have normal blood sugar levels, and there's some chance per year that each one of them will develop diabetes, say, in which case we'd have some stock times this chance per year of developing diabetes, and if there was no one normal glycemic, there'd be no one developing diabetes. If they were all already diabetic. Similarly, if these were diabetics and it was an issue of how many develop end-stage renal disease, there'd be a certain chance per year they develop end-stage renal disease, and if there were no diabetics, and no one to develop, for diabetic end-stage renal disease, then you don't develop that particularly. So you see how it can depend on that then. And by the same token, if there were 1 million people instead of 1,000, we'd be talking about rates of flow that were higher. If this was a stock, was the number of people in the hospital, and this was the mean time they spend in the hospital. If there was 1 person, if there's 0 person in the hospital, and I'm not going to leave. There's no one going to leave. If there's 10, maybe some on average 1 per hour or something like that. Maybe if there's 1,000 people in the hospital, well, putting aside our imagination, there'd be a lot more people than if there were just 10 people in the hospital leaving. So you appreciate that.
Yep.
Yeah. So this is a simple example of a little feedback. We see the feedback sort of graphically, and we see sort of the dynamics associated with it. And you remember that when we first talked about causal loop diagrams and feedback, we talked about how this sort of feedback, what sort of feedback is this? It's a negative feedback. It's a balancing loop, as we call it. We talked about how that sort of loop is associated with dynamics. What sort of dynamics is associated with a balancing loop? It tends towards stability. It tends towards some, in fact, equilibrium value. Ladies and gentlemen, if we have no inflow, what's the equilibrium value of this stock? 0. That's right. Now, so that's good. What if there is an inflow? What if we have an inflow? Call its value I. Good. Excellent. So it'll be an equilibrium when inflow equals outflow. Why? Well, as much stuff, the rate at which stuff is coming in equals the rate of stuff going out. It's like your water shooting into your bathtub at 10 liters per minute, and it's going out of your bathtub at 10 liters per minute. So the level of the bathtub doesn't change, right? Okay. So it's in equilibrium at that point. Now, what happens if we knock it out of equilibrium? How if we were to start a stock so that the value of the stock is much higher than equilibrium? What happens? It'll drain down to what point? Okay, why will it drain? Why was the outflow higher? Because the value of the stock is higher than its equilibrium value. So maybe it's at equilibrium, maybe 10 people per hour coming into the hospital. And at equilibrium, 10 people per hour leaving the hospital. Right? Maybe on average people stay 2 hours in the hospital. Right? Okay. So if we suddenly put 1,000 people in the hospital or something, what would happen is, well, each person leaves on average in 2 hours. You have 1,000 divided, say, by 2, number of hours here, and so we'd have a massive rush and outflow, and that would drain the stock down till it approached once again what? Well, what's the equilibrium value of the stock? If we have 10 people coming in, 10 people leaving, 10 people leaving per hour, if on average they stay for 2 hours, what's the value of the stock that would lead to 10 people per hour leaving? Sorry? 20. 20 people in the hospital. So if we suddenly had 1,000 people in the hospital, started it like that, you'd have a drain down, and it would drain quickly at first, And instead of approaching 0 here, what would it approach? Well, yeah, they would approach a value of 20 for the stock. What would the outflow approach? Approach 10. There's a little feedback. It's stable. You perturb it, you nudge it, you have extra people going to that hospital, it tends to work itself out. Great stability. Again, you have people come into the airport here in Saskatoon with a type of infection that's very, very well managed, well understood. They can get fast treatment for it, and the system responds to them, treats them, and it kind of goes back into an equilibrium. Okay, so this is a first order delay. It's associated with this this stability, and we've seen cases. So if we have a mean amount of time, a delay, the value of the stock is just the value. Suppose the inflow is I. The equilibrium value of the stock will be I what? Will the equilibrium value of the stock depend on the delay? Yeah, in a big way. So what would the equilibrium value be? If the inflow is I, the equilibrium value of the stock will be sorry? E plus A? So okay, so suppose I'll give some hints here. Suppose the delay were infinite. So it approaches infinity. Effectively, what does that mean? There's no outflow. What's the equilibrium value of the stock? It would approach infinity. It goes as high as it needs to, right? It's not. How if the delay were 0? People, what would that mean? I mean, people sort of instantly come out. What would the equilibrium value of the stock be? 0. Is this starting to smell like something? Yes, I times delay. Why? Because if the stock has the value I times delay, what's the value of the outflow? I. I times delay divided by delay, which is I. So the equilibrium value of the stock would then be I times the delay. Good. Good. Now, this delay is the mean time in the stock. Another way to phrase it would be stock times 1 over delay, right? Some coefficient that's just 1 over the delay. It's the same thing mathematically. It's just, the question is, do we want to give a nice name to the delay, or do we want to give a nice name to the 1 over delay? That's all. We could represent it either way. The formula changes from stock divided by whatever this thing is, by the delay, time to stock times whatever variable represents 1 over delay. Does that make sense? So we could say, people with diabetes have a mean time of 13 years before developing end-stage renal disease. Or we could say, on a per-year basis, if we're representing first order delay, on a per-year basis, people have a chance of 1 over 13 of developing end-stage renal disease if they're diabetic. Those are two different sort of equivalent ways of saying that. Or you could say, in a hospital, people have an average time in the hospital of 2 hours. Or you could say, on a per-hour basis, people have a 50% chance of leaving the hospital. Okay? If you're representing this as a first order delay, those are the equivalent. Does that make sense? People comfortable with that? Okay. Silence reigns. Okay, so that's good. So we see, if we have a very fast draining, very fast time constant, in other words, people are in the stock for a very short time, it will drain really quickly. Otherwise, it can drain slowly. I don't want to go over all of this, but for those who are interested, I go through here and prove that the mean time in there is in fact the delay. Okay, so what I'd like to do is I'd like to fire up your Venn sims and let's, ladies and gentlemen, let us go compute. Let us go simulate our first order